All right, welcome back, everyone, to the Deep Dive.
Great to be here.
Today, we're tackling something really foundational in computing. It's kind of the hidden engine behind a lot of what makes our digital lives work smoothly.
Absolutely. We're talking about sorting algorithms.
Exactly. And we're going deep, using some excellent material from Hello Algo as our guide.
It's a great source. You know, you might not consciously think about sorting algorithms day to day,
Probably not.
but they're absolutely everywhere. They're the basic methods for putting, well, anything in order.
And the source gives us a really good framework, not just for what they are, but critically, how to figure out which one you actually need for a specific job.
That's the key part.
Right. So our mission for this deep dive is, to get past just the definition. We want to understand the real impact of sorting. We want to break down the main ways we evaluate different sorting methods and really nail down why there isn't just one perfect algorithm.
Which is a super important point.
Totally. By the end, you listening should have a really solid handle on this core concept and hopefully appreciate the clever balancing acts involved.
So at its most basic level, sorting is just arranging stuff, a collection of data put into a specific order.
Could be numbers, smallest to largest.
Yep, or text alphabetically, or even more complex things, maybe sorting products based on price and rating. Lots of possibilities.
And you definitely see the results all the time. Sorting files on your computer by date modified.
It's sorting.
Or when Google ranks search results.
Sorting again? Even your music playlist, if you sort by artist or album.
But it's more than just making things look neat, isn't it? The reason we do it, the why, is much deeper.
Oh, absolutely. The real power, the necessity of sorting, and our source really hammers this home, is all about efficiency.
Efficiency. Okay.
Ordered data is just dramatically easier and faster to work with. Searching, analyzing, processing, it's night and day compared to a jumbled mess.
So like trying to find a word in a dictionary if it wasn't alphabetized.
Exactly. It'd be practically useless, wouldn't it? Or
Yeah.
incredibly slow at best.
So sorting makes things like binary search possible. Finding something super fast in a huge list.
Precisely. Binary search requires sorted data. It's fundamental for efficient databases. It helps optimize countless other algorithms that need ordered input. It really transforms data.
From chaos to structure.
You got it. Structure that machines can use really, really quickly.
Okay, so sorting is essential for speed and usability, but you mentioned there's no single best way.
Correct. Different algorithms get to that sorted state using very different methods. And because of that, we need ways to compare them, right? To judge them.
Makes sense.
And this is where the source material really helps, breaking down the key dimensions for evaluating any sorting algorithm.
This is where it gets really interesting, I think, because it shows the compromises. You can't always get everything you want.
That's the core trade-off.
So the material lays out several key dimensions. Let's start with the obvious one. How fast is it?
Right, execution efficiency, speed. This usually comes down to time complexity.
The big O notation stuff.
Exactly, like O(n) log n or O(n). You're generally aiming for the lowest possible growth rate as your data set, your n, gets bigger.
Lower's better means it scales well.
Generally, yes. O(n) is often seen as pretty good for typical comparison sorts. O(n) is even better, theoretically the fastest for certain types.
So it's about how the time scales up with more items.
It is, but the source adds a really practical point here. It's not just the big O. There's also the constant perm, or constant factor. Basically, the actual number of basic steps the algorithm performs, regardless of scaling.
So like the raw amount of work per item.
Kind of, yeah. For small amounts of data, an algorithm with a slightly worse big O but a much smaller constant factor might actually run faster.
Interesting. So the theory isn't always the whole story in practice.
Not always, especially for smaller n. But once you get to really large data sets, that big O scaling factor becomes dominant. It's king.
Okay, so you want good scaling and ideally low overhead per item. What's the next big factor?
Memory usage. How much extra space does it need? This is called the in-place property.
In place.
Yeah.
Meaning it sorts the data right there in its original spot.
Pretty much. It rearranges the elements within the original array or list using only a tiny constant amount of extra memory for maybe a few temporary variables.
Instead of, say, making a whole separate copy of the data to sort.
Exactly that. And the benefit, as the source points out, is potentially huge savings in memory.
Which matters a lot if you have massive data.
Massive data, or if you're working on a device with very limited RAM, like maybe an embedded system or a small sensor.
Gotcha.
Plus, sometimes avoiding all that data copying can make it faster too, less memory management overhead.
So speed and memory, the classic performance duo. What about how it, handles the data values themselves?
Good question. That leads us to stability.
Stability, okay.
This one's a bit more subtle. It's about how the algorithm treats elements that are considered equal according to whatever you're sorting by.
Equal elements.
A stable sort guarantees that if you have two equal items, their original relative order is preserved in the sorted output.
The source had a really clear example for this, didn't it, with students?
Yeah, that's a great one. Imagine you have a list of students, and it's already sorted alphabetically by name.
Okay, names sorted.
Now, you want to sort that same list by age, but several students might be the same age, right?
Sure.
If you use a stable sorting algorithm for the age sort, any students who share the same age will still be in alphabetical order relative to each other in the final list.
Ah, so if Alice, age 20, came before Bob, age 20, in the name list.
Then in the stable age sorted list, Alice, age 20, will still come before Bob, age 20. Their original relative order is kept because their ages are equal.
Okay, that makes sense. And an unstable sort wouldn't guarantee that.
Nope. An unstable sort might swap Alice and Bob, even though they're both 20. It doesn't care about their previous order.
Why is that important?
It's critical for what the source calls multi-key sorting scenarios. Imagine sorting contacts first by city, then by last name. You want people in the same city to remain sorted by last name, right?
Yeah, definitely. You need stability for that second sort.
Exactly. It preserves the work of the previous sort when the current sort key is equal.
Very important in practice then, especially with complex data records. Okay, what about adaptability?
Adaptability is about whether an algorithm can take advantage if the input data is already somewhat sorted.
Like if it's almost in order already?
Precisely. An adaptive algorithm can often detect this partial order and finish the sorting job much faster than its typical performance on random data.
So it doesn't just blindly apply the same process regardless. It adapts.
Right. The payoff is potentially a much better best case time complexity compared to its average case or worst case.
So if your data often comes in nearly sorted, an adaptive algorithm could be a huge win.
Definitely. It avoids redoing work unnecessarily.
Makes intuitive sense. Okay, last dimension the source mentions is a fundamental split. Comparison or non-comparison based?
Yeah, this is about the core mechanism the algorithm uses. Comparison-based algorithms are, well, the most common kind.
Like merge sort, quick sort?
Exactly. Bubble sort, too. They figure out the order by comparing pairs of elements. Is A less than B? Is B equal to C? Using operators like ALU.
And the source mentioned a theoretical speed limit for these.
It did. For the general case of sorting arbitrary comparable items, they can't fundamentally do better than ON log n time complexity in the worst case. It's a proven lower bound.
Okay, so ON log n is kind of the target for efficient general-purpose comparison sorts. What's the alternative then?
The alternative is non-comparison sorting. These algorithms don't rely on comparing elements directly to each other.
How do they work then?
They usually leverage some specific property about the data itself, like the range of values if they're integers, or the digits and numbers, or how the data is distributed.
Examples be?
Counting sort, radix sort, bucket sort. Those are the main ones.
And the big advantage here is speed, right? Potentially.
Yes, that's the huge draw. They can achieve ON time complexity linear time.
Linear time. So the time just grows directly with the number of items. That sounds amazing compared to ON log n.
It is theoretically much faster for very large n. You might only need to look at each item a fixed number of times.
So why aren't we using these ON sorts all the time then, if they're faster?
And here comes the inevitable trade-off. The source puts it nicely. Their versatility is relatively poor.
Really?
They often have strict limitations on the kind of data they can handle. Counting sort, for instance, typically works best for integers within a known reasonably small range.
Okay.
Radix sort usually needs fixed-length keys, like numbers or maybe fixed-length strings. They're not the general-purpose workhorses that comparison sorts are. You can't just throw any old data at them that you can compare.
Got it. So potentially blazing fast, but only under specific conditions. Less flexible.
That's the gist of it.
Okay, wow. So let's quickly recap those 5 evaluation dimensions from the source material. We have execution efficiency speed, big O, but also that constant factor.
Right. Then the in-place property, how much extra memory it uses.
Stability, does it keep equal elements in their original relative order? Crucial for multi-key sorts.
Adaptability, can it speed up if the data's already somewhat sorted?
And finally, the basic approach. Is it comparison-based using OCO or non-comparison-based using data properties?
Those are the key lenses through which we analyze sorting algorithms.
And based on all that, you could sort of sketch out the perfect algorithm, couldn't you?
You could imagine it, yeah. It would be super fast, ON maybe, with a tiny constant factor.
You would use basically no extra memory totally in place.
It would be stable, always preserving relative order for equals.
It would be adaptive, flying through nearly sorted data.
And it would be totally versatile, able to sort anything you throw at it.
The dream algorithm, the unicorn.
Exactly. And now for the punchline, the crucial takeaway from the source material. No sorting algorithm that we know of actually combines all of those desirable features.
It just doesn't exist.
It doesn't exist. And that is probably the single most important practical thing to understand about sorting.
So choosing a sorting algorithm isn't about finding the mythical best one.
Absolutely not. It's always, always about understanding the trade-offs. It's about looking at the specific characteristics of the data and the requirements of the problem, as the source says.
Right, so if your main constraint is memory,
you prioritize in-place algorithms, even if they might be slightly slower in some cases.
If you're doing multiple sorts where order matters,
stability becomes non-negotiable. You need a stable sort.
If your data is usually just a little bit messy,
adaptability could give you a huge performance boost. Look for adaptive algorithms.
And if you happen to have integers in a nice tight range,
then maybe a non-comparison sort, like counting sort, is the fastest option, even if it's not versatile.
It forces you to think about what truly matters most for your situation.
Precisely. You weigh these dimensions, you make a conscious choice, a trade-off. Understanding these criteria lets you make smart choices.
And the Hello Algo material sets this up perfectly, right? This whole evaluation framework is the foundation for then looking at specific algorithms.
Yes. The next logical step, which the source goes into, is to take algorithms like, selection sort, bubble sort, merge sort, quick sort, radix sort.
All the classics.
And analyze each one using these 5 dimensions. See where each one shines and where it falls short.
So you can see why quicksort is often used, but also why merge sort might be better sometimes, or why you might occasionally use something else entirely.
Exactly. Context is everything.
Okay, so let's wrap up this part of our deep dive, drawing from the Hello Algo source. We've established that sorting is way more than just tidying up.
It's fundamental for efficiency. Making data searchable, analyzable, processable at high speed, it underpins so much.
And we now have a toolkit, those 5 crucial dimensions, to evaluate any sorting method: execution efficiency, speed, scaling overhead,
in-place property, memory usage,
stability, handling equal elements,
adaptability, using existing order,
and the comparison versus non-comparison distinction.
Right, and the big realization, the core message from the source,
is that the ideal algorithm combining all these perfectly is a myth. It doesn't exist.
Which means choosing the right algorithm is always about trade-offs, about understanding your specific needs.
It moves us from theory to practical engineering decisions.
It really does.
So that leads us perfectly into a final thought for you, the listener, to chew on, directly inspired by this idea of trade-offs from the source material.
Okay.
Since that perfect mythical sorting algorithm doesn't exist, imagine you were designing a system. Maybe it's processing, real-time financial transactions, or maybe it's organizing a massive library of scientific research papers.
2 very different scenarios.
Yes, exactly. Which one or 2 of those 5 evaluation dimensions, efficiency, in-place, stability, adaptability, comparison type, would be the most critical for your specific system? And crucially, why would you prioritize those over the others? What trade-offs are you willing to make?
Yeah, what matters most when the ideal isn't an option? Think about the constraints and goals of your specific problem.
Something to ponder. That's it for this deep dive.